All right. Good afternoon, class, or good morning, whatever time it is when you're watching this video. This is our day 10 lecture video, so I'll go ahead and share my screen as we go over the schedule here. So this is the day 10 lecture, which is going to be used for wrapping up chapter 3. We're going to look at sections 3.5 and 3.6 today to conclude. Then we'll have a bit of a break, and then we'll come back and continue through chapter 4 in day 11. All right. We also have some homeworks that are coming up, homeworks 10 and 11, and those are going to be related to the chapter 3 material that we've covered this week. So if you have any questions about any of that, of course, feel free to email me, let me know, come by office hours, and I'm happy to answer questions about that and try to help you through that process. All right. So we're looking at sections 3.5 and 3.6. A participation question is published for this lecture, so we'll look at that towards the end of the video. But for now, we can go ahead and jump into the material. And for this, before we get into the textbook definition, I'm actually going to go ahead and let's do an example on the whiteboard behind me. All right. So for section 3.5, we want to talk about this idea called conditional probability, where the idea is, well, if I have conditional information or if I have prior information to some kind of random experiment or random event, does that change the likelihood of different events or not? For example, I roll a six-sided die. We've seen this example a few times. Roll a six-sided die, right? And assuming it's a fair die, then each side of the die has a 1/6 chance of resulting from the die roll, right? So the chance of getting a 1 is 1 out of 6. The chance of getting an even number, well, that would be 2, 4, or 6. There are 3 ways to get an even number. And so the chance of getting an even number would be 3 out of 6, or in other words, 1/2, 50%, right? But the idea of conditional information is to say, okay, I roll the dice, but then before you see the result, I cover it up with a cup. So you don't see it, it's under the cup. And then maybe I peek under the cup and I say, oh, this number, it turns out it is less than or equal to 3. So I'm giving you information. I'm changing the game here. Um, so let's let A be the event that I have an even number. And then let's say B is the event where I have a number less than or equal to 3. All right. Now, with conditional probability, the idea is that something has occurred which is prior information to the random event which has occurred. Normally, we'd roll it and then we'd look and we have our answer. But if we roll it, I cover it up and I tell you, oh, by the way, it's a number less than or equal to 3. I'm changing what the possible outcomes are. The probability of A, ordinarily, would be 3 out of 6, or in other words, 1/2, right? That we've seen this before. But if I try to find the probability of A conditioned on B, so this is our notation for conditional probability. So this is conditioned on B, or in other words, you could say this is given B has happened has happened already. Has happened. Oh, I'm running out of space here. Let me move the camera down a little bit. Given that B has happened already. Right? So conditioned on B, or you could think of this as given B has already happened, right? In which case, I've changed things. If B has already happened, this means now the possible outcomes are 1, 2, or 3. Well, in that possible future, if I only have 1, 2, or 3, only one of those numbers is actually even. So now instead of having a 3 out of 6 chance to get an even number, now I only have a 1 out of 3 chance to get an even number. So because we have given information or conditioned information first, this changes the outcome of the thing we're trying to find. All right. This is the idea of conditional information. This is also, fairly common with kind of weather reporting systems, where I could ask, okay, what is the probability it could be rain tomorrow, given that we know the humidity for tomorrow is going to be 20%, or given that we know the temperature for tomorrow is supposed to be 43. If I have other given information, does that change what my prediction is going to become? That's the idea of conditional probability. All right. Now, in the case of this example, the six-sided die, there's only six possible outcomes. I could write out the possible outcomes here and divide it out for myself to find the answer. All right, so that wasn't too bad to do. But if it's a larger example, or if the events are too big, or if I have too many sample points to think about, then how do I find conditional probability? What's my formula here? So for conditional probability, I'm going to erase some of this now. In general, the idea is that the probability of A conditioned on B is the probability that I have A and B divided by the probability of B. Okay. Now, how does this make sense? Let me adjust the camera again. So if B has already happened, then my probability, or my denominator here, is being calculated out of the world that B has already happened. Out of that possibility, as B shrinks the possible outcomes, I have to divide by the probability of B. But the only way A can happen is if, given that B has already happened, well, that would mean at the end of the experiment, both A and B are going to occur, right? Both A and B have to happen. And so if I need both to happen at the same, or maybe not at the same time, but by the end of the experiment, they both have to happen, then I'm looking for the intersection of those two events out of the probability that B has already occurred, out of the world that B has already happened. Look back at the example we just did. A, this was for even numbers. The probability of A was 1/2. B was the probability that we have a number less than or equal to 3. The probability of B is also 1/2, right? But now, as I'm thinking about conditional probability, we already know the answer here was 1/3, but A intersect B, because after all, if B has happened first, the only way A could still happen was if A and B share something in common, which is exactly what we did in that thought experiment. If I have a number less than or equal to 3, that means I have 1, 2, or 3. The only way to still get an even number is if I got a 2. That's the intersection between A and B here. In which case, the probability of the intersection, well, ordinarily, that would be 1 out of 6, right? But for conditional probability, if I say B has happened first, I no longer have all 6 possible outcomes. The fact that B has happened first is changing, the denominator is changing the possible outcomes. And so for this calculation with the formula, I could write this out as, well, the probability of the intersection is 1/6. The probability of a half of B is 1/2. But recall, dividing by a fraction is the same thing as multiplying by the reciprocal. I would have 1/6 times 2, or in other words, 2/6, which is the same thing as 1/3, which, no surprise, we already knew 1/3 was the answer. But in general, this formula here then gives us a way to calculate any conditional probability where if I can find the probability of their intersection and the probability of the conditional information, create a fraction of that to get my final answer, and then this is going to be our general rule anytime we have a conditional probability sort of question. right. So we have this here for us. I'm going to switch back to the screen for the textbooks. Let me share my screen again. All right. And so here's our definition for conditional probability. Probability of A conditioned on B is the probability of their intersection divided by the probability of B. All right. Now, they give us this first example here where this is different from what we just did, where I would list out all the possible sample points. But if I'm taking a survey of, hundreds or thousands of people, then I don't want to list all the sample points. That's going to be a lot of work, right? So consider this example. To develop programs for business travelers staying at convention hotels, Hyatt Hotels commissioned a study of executives who play golf. The study revealed that 55% of the executives admitted that they had cheated at golf while playing golf. Okay. Also, 20% of the executives admitted they had cheated at golf and had lied in business. Okay, well, so what? What does this really matter for us? We can create a conditional relationship here. Let A be the event that someone cheats at golf. The probability of that event, according to the survey, is 55%. The probability that somebody lies in their business dealings, um, well, we're not given the probability of B in this question, but we are told the probability that they do both. The probability that they cheat at golf and lie in business, that's the intersection of A and B, its probability is 0.2. So we have this information. So then based on our conditional probability formula, we could ask the question, well, what is the probability somebody lies in business given they cheat in golf? Because the reality here is, a lot of people, they might be willing to admit that they cheat at golf. It's just a game. Who cares? But lying or cheating in business, that could be a more serious thing or even possibly a crime, depending on the situation. So they might lie about whether they actually cheat in business, right? Or lie in business. However, the conditional probability shows us a little more information here because this is asking the probability that someone lies in business given they cheat at golf, right? Because I might see somebody out at the golf course, maybe he's the CEO or something, and he's cheating while he's playing golf. And the guy claims to be good at business. He claims he doesn't lie in business, right? But what is the probability he does lie in business if he cheats in golf? Well, we calculate here, same formula, same calculation. The probability of their intersection, that's both, is 0.2, 20%. And I'm dividing by the conditional information. So here, A is the conditional, and so that is in the denominator. So out of the probability that they cheat in golf, I see them cheat in golf, but now I want to know, well, because I know that they cheated while playing golf, what's the likelihood that they also lie in business? 0.2 divided by 0.55, we see now this probability is 0.364. So this is a little bit more revealing, right? Before, the probability that someone cheats in golf and lies in business at the same time, that was only 20%, right? But what if they're lying about that? So this tells us that if we see somebody cheating in golf, the likelihood that they also lie in business actually has gone up here. It is more likely that they also lie in business if they cheat while playing golf. So kind of this interesting correlation business, all right? Now, we do have to be careful anytime we're trying to make predictions or generalizations with statistics, right? We've talked about this back in chapter 1. This does not mean that somebody who cheats in golf is guaranteed to also lie in business, right? Correlation does not mean causation. Just because someone cheats in golf does not mean they cheat in business. All this is telling us is that if someone cheats in golf, it is then increasing the likelihood that they also cheat in business. That's all that's telling us here. Okay? So we got to be careful about the implication here. We see that there is a correlation between cheating in golf and business, but this does not mean causation. All right? It just means an increased likelihood. Okay. So this is 3.5 for conditional probability. We also have this smoker example that's kind of interesting to look at. So they sample a bunch of different people and they're trying to determine, okay, do these people smoke and do they have cancer? So someone who responds yes to both, this means that they are a smoker and they currently have cancer. If they do not, or if they smoke and do not have cancer, then they're in this top right category. If they do not smoke and they have cancer, they're in the bottom left. If they don't smoke and they don't have cancer, in the bottom right. Okay. Now, at first glance, this looks like, um, well, in terms of who's got cancer, only a total of 8% of the people in the survey even had cancer, right? So on one hand, doesn't seem too dangerous. Um, we also see that, well, there's also a number of people who smoke and do not have cancer, right? But again, let's think about the conditional information here. So what would this mean? If I say probability of A conditioned on B, well, what is this really asking here? In word form, this is probability that someone is a smoker. So probability that some random person X is a smoker given they have cancer, right? Now, this table does not immediately tell me the answer to this kind of question. What this does tell me, though, is the intersection of this stuff. The probability that someone is a smoker and has cancer, right? This doesn't tell me given information. But from our formula, we know that we would need the probability of both, and then that would be divided by the probability of the person having cancer. So X has cancer. All right. Well, in total, the probability of having cancer, there are two different ways to have cancer in this survey. You could have cancer and be a smoker, or you could have cancer and not be a smoker. But the probability of someone having cancer, in other words, the probability of B here, well, this is determined by all of the different ways B can occur. We could have that they have cancer and they're a smoker, or they have cancer and they're not a smoker. Either way, if we add them together, because there are two different ways for B to happen, this means the probability of B is 0.08. Okay. Now the probability that someone does that has both, they are a smoker and they have cancer, well, that's A intersect B, or in other words, both A and B are happening at the same time. That's the top left. That would be 0.05. All right. But now this is a little bit more interesting. So what does this question actually say? The probability of A given B. So given somebody has cancer, what are the odds that they're also a smoker? So this would be zero point zero 0.05 out of zero point zero 0.08. But when you put this into a calculator, um, hold on, my phone is in the other room. I'll be right back. All right. So we go to the calculator. 0.05 divided by 0.08. Well, now we have 0.625, or in other words, 62.5%. That's huge, right? Again, what is this saying? This is saying, given someone has cancer, take a random person who has cancer, what are the odds that they also smoke 62% chance that they also smoke. That's a huge correlation here, which at first glance does not appear just by looking at this table, right? This is also where conditional probability can sometimes be more revealing. What if I flip the two here? Let's say probability of B conditioned on A. In word form, this would mean the probability of a random person who has cancer, or no, the probability of someone having cancer. So the probability X has cancer given X is a smoker. All right. So now my denominator, if I'm conditioning on A, I need the probability of A. Well, the probability of A, if someone is a smoker, in this survey, there are two different ways to be a smoker. You could be a smoker with cancer, or you could be a smoker without cancer. Adding them together, then, there is a total of 0.25% chance that someone is a smoker in this survey. All right, 25% of the people in the survey are smokers. We already know the probability of both is 0.05. We did that earlier. And so now the probability of B conditioned on A can be calculated as, well, the probability of B, or sorry, the probability of both, which we already know is 0.05, out of the probability that they are a smoker. That's my conditional. I divide by the conditional. That would be 0.25. Well, now we get an answer of 0.05. We go to a calculator, divided by 0.25, and we get 0.2, or in other words, 20%. So what is this saying? This is saying, given you take somebody who is a smoker, what are the odds that they have cancer? All right, well, there's a 20% chance they have cancer, which at first glance, all right, so then is smoking so dangerous? I mean, if I take a random person who's a smoker, there's only 20% chance he has cancer. That doesn't seem too bad. We can also flip the question here. What if I ask about the probability of not having cancer? So B complement. So I'm using the upper caret symbol to reference an exponent. This is B complement, in other words, not B, given A. So in word form, this means I would be asking the probability that a randomly picked person, X, has no cancer, given X is a smoker. Okay. Now this is a different question. So here, so look at the probability. I'm going to need the probability of both, which is going to be different here. So I'm looking at no cancer and a smoker. In which case, all right, no cancer, that's the second column, and they are a smoker, that is 0.2. So I have 0.2, okay? Probability of A, we already know is 0.25. So now we look at the question here for our calculation. The probability of B complement given A is the probability of both, where they have, so this is someone with no cancer, or they do not currently have cancer developed, and they are a smoker, is 0.2. All right. So that is my numerator for our formula for conditional probability. This is divided by the probability of A. Where, let's see, we divide by the conditional, that's probability of A, 0.25, and we get here that we have 0.2 divided by 0.25, and we get 0.8. All right. Or in other words, 80%. So if you take somebody who is a smoker, given that information, take a random person who is a smoker, there's an 80% chance they don't have cancer. Well, hold on a moment. This sounds like smoking's not so bad. Maybe it's okay. Maybe that's safe. Maybe we don't have to worry about it. Okay, well, hold on to that thought. Let's continue the question here. We can ask the same question of, well, what's the chance of somebody having cancer if they are not a smoker? So, last one we'll look at here with this table. Let's say we calculate the probability of somebody having cancer given that they are not a smoker. So a complement is now um, my conditional information. So what we're trying to see is if I am not a smoker, then is that going to change the chances of me having cancer, right? We see up here, we did this earlier, the probability of someone having cancer given that they are a smoker was 20%. Well, what's the probability of developing cancer given I'm not a smoker, right? Probability. So in regular word form, this is a random person X has cancer given they are a smoker. All right. Well, the probability of both, that's B and not A, right? Here, the probability of both, we're looking at B and not A. So that means yes, they have cancer and they are not a smoker. That is 0.03, so pretty small there. Okay. The probability of, so for the conditional here, we're looking for the probability of a complement. In other words, probability of not being a smoker. Well, there are two different ways to be not a smoker. You could be not a smoker with cancer, or you could be not a smoker without cancer. Add together, that is 0.075, right? So now we can calculate this conditional probability. The probability of developing cancer given somebody is not a smoker is 0.03 divided by 0.75, and we get an answer here now of 0.03 divided by 0.75 of 0.04, or in other words, 4%. Now this is telling. Now this is actually starting to give me a picture here. So, let's see. I should have a highlighter here somewhere. Thought I did. Oh well. So yeah, look at the difference here. The probability of someone having or developing cancer if they are a smoker is 20%. But the probability of someone developing cancer if they are not a smoker is only 4%. So while sure, maybe the 20% looks small, but in comparison here, if someone is not a smoker, there's only a 4% chance they're going to develop cancer. In other words, if you do smoke, you are 5 times more likely than a healthy person or than a person who doesn't smoke. You're 5 times more likely than a non-smoker to develop cancer. That's a huge difference. 5 times more likely, even though this is 20%, that's, much more likely to happen than a 4% chance, right? So now we have a better, clearer picture of what's being said here by looking at the conditional probabilities, where at first glance, this table doesn't tell me that kind of information, but we can calculate that information by using our formula for conditional probability. All right. So that's kind of the big, take home for how we can use this formula in an application for studying statistical information in the real world. All right. So let me go ahead and clear the screen here. And oops, that didn't do it. Here we go. Clear all the drawings. All right. So this wraps up section 3.5. What we next want to look at is 3.6. This is a section dedicated to what is called the multiplicative rule. All right, how does this rule work? Well, first, let me go to the whiteboard here. So I'm going to turn off the screen share. And we'll go back to the board. So what is the multiplicative rule for probability? Well, first, recall our formula we had here for a conditional probability. The probability of A conditioned on B equals the probability of both divided by the probability of B. So where do I get my multiplicative rule? Well, just multiply the denominator over to the other side. And now we get a multiplicative rule or a multiplicative property. Multiply P of B to the left. And we now have the probability of the intersection of two events could be calculated as the probability of B times the probability of A conditioned on B. We call it the multiplicative rule because we have this multiplication in the probabilities here. All right. But interpretively, what does this mean? Why would we care about this kind of rule? What is it doing for us? Well, on one hand, when we're trying to calculate the probability of an intersection, which so far in our last few examples, that might not be too bad to do by itself. Maybe it's given to us in the information. But sometimes this isn't given. We might have to calculate it. All right. Well, when we say A and B, right, since the intersection is just like the word and, we can think of it as a chain of events. If I say find the probability of A and B, that means as a chain of events, well, I could think of it as B happens and then A happens given B has already occurred, right? If I have B happen and then A happens, that means both happened at the end of the experiment. I can think of it as a chain of events in this regard, where I have the first guy times the second guy, where the second guy is happening after the first has happened, given the first has happened. Okay. But I can also flip around the order here. Since, after all, for conditional probability, I could switch the order that I'm conditioning on, right? I could say probability of B conditioned on A. Well, that's still the same intersection, but now it's divided by A instead of being divided by B. Well, multiply to the other side, we see that the multiplicative rule can be written in either fashion. Either B happens first and then A conditioned on B, or maybe A happens first and then B happens conditioned on A. Either way, the conditional probability formula gives us this multiplicative trick where in order to calculate the intersection, I can write it as a multiplication of these two properties or probabilities, and I can write it in either format, and it's going to work out. It's the same thing, since after all, I'm using the same formula. Okay? So to kind of see this play out, we do have some other examples from the textbook. In particular, we want to consider um, yeah, let's consider this example with the dice again. So let me make some room, write down these formulas somewhere. We're going to use them in a moment. All right. Now, on one hand, this example, because I'm using a six-sided die, it's intentionally kind of a simpler example so we can more easily write out what's happening. But the same principle can apply even when it's a more complicated situation. Okay? So let's roll a six-sided die, a fair six-sided die. Roll a fair six-sided die. Okay? Let A be the event that we have an even number. Even number. So similar to what we did earlier, but we're going to change it a little bit. Let B be the event that we have a number which is less than or equal to 4. Okay. Now, sure, It's easy enough to calculate these probabilities. It's not too bad to do. Half of the numbers are even. The probability of A is 1/2. For B, well, a number being less than or equal to 4, there are 4 numbers out of 6, right? 4 out of 6 is the same thing as 2/3. So we have that, okay? But now as we start thinking about this multiplicative rule, right? What did that say? The probability of the intersection is equal to, I could write it as a chain of events where A happens first, followed by B given A, or vice versa. I could write it as B happening first times the probability of A conditioned on B. It's going to work out the same way either way, but we're just checking to see what happens, okay? And we're actually going to see this is a funny example where some other special characteristics are going to pop out, but we'll hold on to that for a moment, okay? Now, first, if I were just trying to calculate this ordinarily without using this formula, A intersect B, I'm looking at even numbers which are less than or equal to 4. Well, there is 2 and there is 4, right? So that's 2 possible numbers. A intersect B is a set containing the sample points 2 and 4. So the probability of this intersection is 2 out of 6, or in other words, 1/3. So we already know what the answer is supposed to be, but forget about for that moment. Suppose we didn't know that answer. Do we get the same answer with our formula? Well, the probability of A, we already know, is 1/2. The probability of B given A. Now, this is a little bit different, right? Given A has already happened. So given an even number has occurred, that means I have a 2, a 4, or a 6, right? So there are only 3 possible outcomes that can happen there, 3 possible results. But if I'm looking for a number which is, in the case of B, less or equal to 4, that would be 2 or 4, right? 2 or 4. In other words, that is 2 out of 3 possible outcomes. If A has already occurred, there are only 3 things that can happen. But for B to still happen, that's 2 out of 3, right? But lo and behold, look what happens here. 1/2 times 2/3 does in fact give us 1/3 as an answer. This formula works and we get a correct answer. This is true. All right. So this works out using our multiplicative rule. However, something interesting also has happened here. Look at the probability of B given A. The probability of B given A is equal to 2/3. But the probability of B was already 2/3. So the funny business here is that this is an example where, regardless of whether A happens first or not, the probability of B was still 2/3. It didn't change anything, right? Probability of B is 2/3, and even if A happens first, the probability of B is still 2/3. It doesn't change the probability of B. Well, what if I flip the order, right? Let's see what happens. What if I think about the reverse direction? What about A conditioned on B? If B happens first, is that going to change the probability of A? We already know the probability of A is supposed to be 1/2, and that's where, if from the very beginning, we don't know if B happens first or not. Okay? Well, for our formula for conditional probability, this is the intersection divided by the probability of B. Well, the intersection, we already did that earlier. A intersect B is 2 and 4. This would be 2 out of 6, in other words, 1/3, divided by the probability of B, which is 2/3. But recall, dividing by a fraction means multiplying by the reciprocal. 1/3 times 3/2, and we get 1/2, which is still the same as the probability of A. Okay, so this is different. In the last examples that we did previously, when I had the probability of A, but then conditioned on B, that changed the likelihood of A. That changed, well, out of the world where B has happened first. Now, how likely is A? But in this specific example, regardless of whether B happens first or regardless of whether A happens first, the probability of B is still the same. Probability of A is still the same. It didn't change, right? This is actually a special property called independent events. And so we had the same definition in the textbook. A and B are called independent if the probability of A conditioned on B is still the probability of A. Regardless of whether B happens or not, whether B happens first or not, it's not going to change the likelihood for A to occur. All right. Now, we also want to be careful with the vocabulary here because at the end of the last lecture, we were talking about when two events are mutually exclusive, that means their intersection is empty, they're separate from one another, they don't share anything in common. All right. Being independent and being mutually exclusive are two very different things. All right. They're different words, they are different vocabulary terms, and they do not imply each other. Take this example. A and B here are not mutually exclusive, right? They share numbers in common. Their intersection is not empty, but they are independent, where regardless whether B happens first, it's still the same probability A, okay? So you can have events which are independent and not mutually exclusive, okay? So yeah, we just want to be careful here. Where mutually exclusive and independent, they are different words, they have different meanings, they do not imply each other. Okay, so be a little bit careful here with the wording. Um, so we have that example to showcase here. All right, great. Now, one other last point to highlight here is that if two events are independent, then that means their conditional probability is really just the same thing as the original event, right? The probability of A conditioned on B is just A. So when we have independent events, this changes our multiplicative rule. In what way? Well, let's back up. Let's look at the multiplicative rule again. The multiplicative rule stated that the probability of A conditioned on B is equal to the probability of A times the probability of B given A has already occurred. Think of this as a chain of events, okay? Where I have A happens first and then B. But if A and B are independent, well, what does this do to our calculation? If they are independent, then regardless of whether A happened first, the probability of B conditioned on A is just going to be the same as B, right? Whatever I condition on, if they're independent, that conditional piece doesn't matter. The probability of A conditioned on B is just A. So in the same way, if they are independent, then conditioning on A doesn't matter. The given part, the conditional part, doesn't matter. In which case, this intersection can be written as just the multiplication between the probability of A times the probability of B. As a chain of events, it's just one after the other, and I don't have to worry about the conditional piece because they are independent. All right. Classic examples of this would be like a coin flip situation. When I flip a coin, I could get heads or tails, right? The second time I flip the coin, I could also get heads or tails. Regardless of the result of my first flip, right? If my first flip is heads, well, my second flip it's still a 50-50, right? Regardless of what happened the first time I flipped the coin, the result of that first coin flip is not going to change or affect the probability of the second coin flip, right? Each time I flip the coin, it's still a 50-50 shot for it to be heads or tails, all right? So this actually brings us nicely into the participation question. So we can go into Canvas, look at participation day 10. Let me share my screen here. Okay. So suppose I flip a fair coin and you flip a fair coin. What's the probability we both gets heads? Well, these are independent events. Regardless of what happens with my coin flip, that's not going to affect or change the probability for your coin flip. So I can think of them as independent events, and I can use the multiplicative rule here. All right. So the probability, so let's let A be the event. So this is the event where I get um, heads on the coin result, and B, let's let this be the event uh, where you get heads as a result. Okay. These are independent events, right? So the probability of both of these things happening together, the probability of A and B, we're talking about both happening. This is an intersection between the two events. Well, then, because they're independent, it's the probability that I get heads times the probability that you get heads. Well, this we can already calculate for ourselves. The probability that I get a heads, it's a 50-50 shot, right? This is 0.5 times you also have a 50-50 shot. We get a final answer of 0.25 for today's participation question, all right? 0.25, or you could write that as 25%, okay? But to think of this experiment as another way of thinking about it, we've seen this example before where if you flip a coin twice, there are 4 possible results. 2 heads, 2 tails, heads, tails, or tails, heads, right? 4 possible results. The result where we both get heads, so that's only one possible outcome out of 4. 1 out of 4 is the same thing as 1/4, 25%. So what we see here is that the same question we could have answered already based on what we knew at the beginning of chapter 3. But we have this kind of same question repeated, and we can answer it using what we know about intersections, using the multiplicative property, using what we know about independent events. So as we continue in probability, as we continue in statistics, we oftentimes find, yeah, in fact, there are multiple ways of how you could go about solving some probability or statistic question and arrive at the same final answer. They're both equivalent methods for thinking about the same question. All right. So that's our answer for today. Of course, if you have questions about it, feel free to email me, come by office hours, let me know. This will conclude chapter 3, and so conclude our material for this video. We do have some homeworks that are coming up, so by all means, let me know if you need help with any homework. Otherwise, that will be the end of this video, so I'll turn off my screen share. Best of luck, enjoy the break, and if you have questions, let me know. Otherwise, have a good rest of your day or have a good night. I'll see you in the next video.